vectors, and similar work like what we just showed with hexagons and squares, where it was shown that these patterns bifurcate transcritically from a featureless state. There. Okay, so now we start a new topic, related to the old topic. We're going to talk about instabilities of roll patterns. I alluded to this before. If you remember, we talked about the Busa balloon, and this is in three-dimensional space of wave number. Okay, now we're talking about, maybe there's no, oh no. I think everybody's supposed to go to the other thing, the seminar. No, isn't that the ringing for the seminar maybe? No? Come to the seminar?
The bell tolls. Proof is Stephen.
Okay, so of course we made a lot of pictures like this, right? Many, many pictures like this. But after all, these things can then undergo bifurcations. And then they can undergo bifurcations, and who knows what else. Lots of things can happen. So what Busa's balloon describes are the instabilities of rolls. This was really among the first time that real fluid flows, I think, were calculated by real. He was right there in the beginning, in the mid-60s or so, doing this. So this is the instability. You have these rolls, two-dimensional rolls. Okay, and he calculated the calculation we did, of course, is easy. We did it for pedagogical purposes. We did free slip, top and bottom, and we found the eigenvectors. But we didn't go very far after that, hardly at all. We went to the Lorentz model, where we did the first nonlinear interaction of eigenvectors with each other. We added one term, right? We had originally, when we did the stability analysis, we had the temperature and the stream function, but then we had another kind of temperature, so we had three. The Lorentz model has three equations, everybody knows that. Okay, but this is much harder. This is not, he just did the calculation of the rolls. The rolls in the non-free slip case, completely non-linearly treated, and those were, Hugh, do you think those were the first hydrodynamic proper hydrodynamic calculations?
So.
What Busa did? Of rolls and their instabilities, and that was wasn't it in the early 70s, late 60s? Could people do much like that? You're in a different world from me, this aerodynamic world. But were people doing real 2D, true 2D calculations then?
No, because they were just it was simplified equations.
It's too simplified.
Yeah.
Yes. So he's really was really a great pioneer. And so he was taking these now, the rolls, as the new state, and doing linear stability analysis about the new rolls. Okay, and the different kind of perturbations that he was putting on to the rolls are those described there by those words, and so I've tried to show some here. This is called skew varicose, and in the ideal case you would see this longer, and this is in, out. You see it's a pinching here, and here's a pinching. So in the idealized case you would write, you probably would do something like this, and then you would do something, if I did it properly, I would do something like, right, something like that. That's what that represents a little bit of. And then you can see that these rolls are unstable to forming rolls in the other direction. You'll notice that their wave number is larger, their wavelength is smaller. Anyway, there's a whole catalog of this, as you can see. This, and we put them together, make the Busa balloon, and it's only within the this Busa balloon that the straight rolls are stable. Otherwise, you exit. That's to say, it depends on your wave number too. If your wave number is too large, you're unstable. And that's there. That's what he did. We're going to study two of the instabilities. We're going to study Eckhouse and zigzag. We're going to study them actually quantitatively. We can get pretty far with that. We will study them with the help of the Newell-Whitehead-Segura equation. That's like the Swift-Hohenberg equation, but simpler yet. The Swift-Hohenberg equation, you don't know what is going to come out. It's like Navier-Stokes. You run it, and then you solve it, or hexagons or not, or whatever. This is an equation where you know what you're looking for. So he's going to write, you start with, say, something like Swift-Hornberg, and you have a function, you have u of x, y, and t. And now you represent it as a of capital X, capital Y, capital T, times this e to the I qcx describes waves. Waves with wave number qc, wavelength 2 pi over qc, and in the x direction. Okay? And you use the method of multiple scales, which again, if you were, what do we need now, 2018, if you were studying, let's see, when was I studying? I didn't have to learn this, but I'm just barely. I was studying in the late 70s, early 80s, and that was still considered the normal way to study things was by asymptotics, but I was just about one of the first to not have to do that and to do everything computationally. So if you were learning in the 60s or before or the early 70s, you would have learned the method of multiple scales. You might have learned it even anyway, and you would all be doing this. So using Swift-Hornberg equation and applying the method of multiple scales, you get this other equation here, which may look a lot to you like the other one, but it's different. One of the ways that it's different, you can tell right away, is it's treating x and y differently before we had a Laplacian. Why would it treat x and y differently? Well, that's because it's studying the instabilities of rolls in the x direction. So x and y are very different. X is the direction of the rolls. Y is the direction in which there was nothing. It was homogeneous before. That's the direction along the rolls. So x and y are very different. Okay, so we're going to study this equation now. And also its meaning is different. Besides the way it looks, its meaning is different. When you have a before, when we did Swift-Hornberg, when we had u constant meant that there's nothing. Here, a constant means we have rolls. That's what a constant means, because it's something that multiplies the rolls. And when we have rolls with the wrong or off-critical wave number, that's when we have e to the I qx. And this q is not the wave number of the rolls, it's the deviation from criticality. So q positive means that you're going to have rolls that, say, qc plus q is bigger, so the rolls are skinnier than their preferred value, and qc, and if q is negative, that means that's qc is less than qc, so that's fewer rolls, so they're wider than their preferred direction. Okay, so now you understand what it means, and you see that they look different. Okay, so let's just do that. Let's look for linear stability of A equals 0, uniform basic state. Okay, we're not starting with the rolls yet. We're going to get the rolls, and if we put in u of e to the I qc plus qx, that gives us rolls of whatever wave number, qc plus q. That gives us a q. The amplitude a is e to the I qx. So that is how we represent something that has wave number qc plus q is by a, that's e to the I qx. Okay, another difference, well, that's there. You see that if you're doing linear stability analysis around the flat state, as usual, you're concerned with mu minus a squared as the amplitude here. That is to say, I think I'm saying several different things. I think I'm saying them wrong. Excuse me. Sorry, hold on just a second. Yeah, I'm saying things wrong. Stop. We're going to study linear stability about a equals 0 before there are any rolls. So we're not concerned with the cubic term. We're only concerned with this term here, this differential term, and we have mu minus q squared, because this is the eigenvector we're putting in, q squared, that's dx squared gives us minus q squared, so mu minus q squared a. And we check to see when that hits 0, and that is when mu c is equal to q squared. So successively, as we explore different q's, more and more of them bifurcate, meaning we have a 0 eigenvalue, more and more of them bifurcate as mu goes up. We saw that picture a while back. We saw this picture here. There. As we increase mu, we have bifurcations with different q's. Okay. So that's what's being looked at here, and we can calculate even their amplitudes, because this term, you'll remember the kind of calculation we're doing for the hexagons and so on, if you write e to the iqx times e to the minus iqx, that gives you 1, and you're just now looking for mu minus an amplitude squared minus q squared equals 0. So you even get this amplitude, the saturated amplitude. It's like when we did the pitchfork bifurcation, we got x equals plus or minus square root of mu. Except here we have a spatially dependent term, e to the iqx, but that's just giving us a minus q squared here. So we get these exact solutions for this simplified equation. Okay? So everybody see, understand we have these, this picture, this is, so far what this is describing is this. This is mu, and these are differential, this is A, and these are different Q's. This is a certain Q, this is the next Q, this is the next Q, this is the next Q. As you increase mu, you allow more, you have more and more. Each time mu hits one of those Q squared values, you form a new branch. Okay. Now, okay, we have everything that we need because we have the value of the new branch. We have its amplitude. We have this functional form here. It's not just schematic. We know what it looks like. Its amplitude is this. So we can do linear stability analysis using this equation of this. The linear stability analysis about 0 was easy. We just did it. And now let's do it about this. So we substitute AQ plus e to the sigma t times some function of x and y into this equation. NWS, it stands for Newell Whitehead score. The people who. So as we said before, all of the linear terms just get translated down. So we have, just as we had mu big A here, now we have mu on little a. D by dt becomes sigma A. This is a linear term, so it just stays the same. The only thing is this term, we want to write a squared A, and let's see, is there an eraser? This is an eraser. So we want to write AQ e to the I, sorry, AQ plus A e to the iqx. So hold on just a second. I'm in trouble here. AQ e to the iqx plus your arbitrary A here, and we're going to do this times this squared. And what do let's see, am I going to get in trouble like before? I think everything is supposed to be multiple. There's an e to the iqx in front of everything. Well, let's see what happens. We get, I think maybe I don't want this here. Maybe it's in front of everything, I'm not sure. Anyway, we get AQ squared AQ. We get AQ squared AQ. We get AQ squared AQ, so we want to do this and the complex conjugate and that, and then we want to do sometimes this, I get another, don't I get an AQ? Yes, I get an A, yes, right, the A's, yeah. This I get, fine, and then I have AQ squared A, and then I have AQ, why did I start this? AQ squared A star, and then I have A squared A, and I think that's all. Do I have other terms? No, I probably have other terms here. I probably have A squared, no, I think that's all. Is that true, or there are other terms? there seem to be two of these. And these are the terms that are linear in A. The A cubed term gets dropped, and so what we need to do is to solve this linear equation. We need to find out when sigma is positive. Changes sign. Okay, so we can first investigate changing only the x, having A depend only on x. And in that case, we're only concerned with changing the wavelength. We're changing, the e to the iq. We saw before that some of these seem to wish to change the wavelength. The wavelength here is different from this, and that is what the system is trying to do with some of these instabilities. So we introduce the eigenvectors that only depend on x, and we have either those that have the same wave number as the original one, or that have a different one, and we have plus and minus, and we need plus and minus, because we're going to have an A star here. If we just did e to the I q plus k, we would have e to the I minus q minus k. We would have no hope of satisfying everything. So when we set our other eigenvectors like this, and we substitute this into the equations, or we substitute the 0, 1 into the equations, we get equations for the coefficients alpha 0 or alpha k and beta k. Let's start off by doing this with alpha 0. We get merely the equation e to the minus mu minus q squared, and then we get another mu minus q squared for alpha naught star. And we put those together, and we learn that we have two eigenvalues here. And you've seen this before, this Jacobian. You've seen it, of course, for a circle pitchfork. What is this saying? This 0 is saying this is the phase direction, and this is saying it doesn't care. It's saying that when you look at the instability of a roll to moving, it doesn't care. This now, this minus 2 mu minus q squared, you've seen it before. This is the instability, this is the amplitude eigenvector. And what this is, okay, so I show you in pictures, I show you, what this is describing is the transition from this to this circle pitchfork. And this has a 0 eigenvalue along the circle, and it has a negative eigenvalue. You can see that this one is negative because this branch only exists when mu is greater than q squared. It has a negative one here and a 0 one here, and the negative one is that it likes a certain amplitude. If you change its amplitude, then it will come back. But if you change its phase, it won't. And that minus 2 you've seen before also, because you've seen many times the equation x dot equals mu x minus x cubed. You've seen this, the steady states, 0 equals fx bar, and then you found that x is equal to 0 or plus or minus square root of mu.
X bar.
The steady state, right? Then when you did, just to do the stability, you would do fx bar, which is equal, well, you just write f prime of x is equal to mu minus 2 minus 3x squared. Right, everybody remember that? And then, so f prime of 0 was equal to mu, so it went from being negative to being positive when you crossed mu equals 0. And f prime of plus or minus square root of mu was equal to mu minus 3 mu. Everybody remember this calculation vaguely? Which is equal to minus 2 mu. And that's the same minus 2 that you see here. Okay? That's the same one. It comes from just all this. You know that the rolls were formed by circle pitchfork. And all pitchforks have this property that this eigenvalue is 0 at the point that it's formed, and it becomes more and more stable. Here, that eigenvalue is 0, and here it becomes minus 2 mu as you go up and down the branches. It's that same minus 2. Okay, so we understand this. This is not the Eckhouse instability. This is just, it's just like when we did period doubling. When you look for a bifurcation, you find the bifurcation that formed the state. This is the bifurcation that formed the state. These are the properties of a circle pitchfork, and a circle pitchfork form the rolls. Now, we're in a position to look, are the rolls unstable to something else? So we change the K, and then there's a lot of arithmetic here, blah, 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 blah. We write, remember, AK as a sum of Q plus KX and Q minus KX. We substitute, blah, blah, blah. This is why we need a beta, because we're going to have a star, and so this is going to become minus Q plus K, and there's going to be cancellation, this, that, and the other thing, and let's not go through it. What you end up with, just as before, we ended up with this as the Jacobian matrix. Now, for alpha K and beta K, we end up with this as the Jacobian matrix. And that may look complicated, but in fact, it turns out to be a very simple matrix. You can see already the off-diagonal elements are the same. The diagonal elements are almost the same. They differ by 2qk, and it turns out to be easy to find their eigenvalues. We'll call that formula. The formula says that the eigenvalues of a 2x2 matrix are the average of the diagonals, and that's easy to take. Just get rid of this thing here, right? It's just this. Right, the average of the diagonals, which is just this term, plus the square root of the difference between the diagonal elements over 2 squared. So that's just this term here, the difference. That gives you 4kq over 2 gives you 2kq, and you square that. And then you take the product of the off-diagonal terms, and that's there, and hopefully you do all that, and you get this formula here. These are the eigenvalues corresponding to these eigenvectors, and the eigenvectors, we're looking, they're supposed to be perturbing this big A. So here we are with those eigenvalues. Now, we're going to vary mu. We're going to take Q's to be, excuse me, there's 2 of them, so there's plus and minus, and we're going to fix Q to 1. We're going to look for rolls with wave number 1, meaning wavelength 2 pi. And we're going to vary K, this index K. The point of bifurcation is here. And this is when you can see here the eigenvalues we talked about before. The 0 plus and the 0 minus. This one is the marginal one, the one that tells you we don't need to go around the circle, we don't care about our phase. That's this one. And this one is that minus 2 one. Okay, so these are the 2 that we were discussing here. Sigma naught 0 and sigma naught minus 2 mu minus q squared. That's part of the spectrum. It's here, it's the green ones. Now, that was for k equals 0. For k equal 1, we just substitute k equal 1 into this formula. We substitute q equals 1 as well, because we take q equals 1. And we vary this with mu, and we find 2 eigenvalues here. There were 2 red ones. And then for k equal 2, we also find 2, which are in blue. Okay. Why is that one 0, I wonder? I'm not sure. Okay, but what we're concerned with right now are the red ones. This red one is going to cross 0, and we know that when an eigenvalue crosses 0, something happens. Right? This eigenvalue, but it doesn't go in the direction that we usually go into. This goes from positive to negative as we increase mu. So we put all this information together, and we get a picture like this. Okay, so let me tell you about this picture. Well, actually, there's a little bit more math here. Let's see. No, let me show you this picture here. What is this picture? This first parabola is mu equals q squared. Mu equals q squared. Where have we seen that before? We've seen it here, mu equals q squared. This is the point at which at A equals 0 loses stability to rolls. Mu equals q squared. Rolls of different amplitude, of different wave numbers, e to the I qx. So mu equals q squared is when the rolls are created. Let's go back here, and I think we saw it before also didn't we make this picture in the convection class? Okay, so that's this. The reason we have these lines here is because we're going to assume a finite box so that all of our allowed q's are multiples of 2 pi over q. But don't think about that right now. Just think about the fact that this thing here, this parabola, is where you create rolls that have wave number q. So the critical one, the lowest one, is here at q equals 0. Remember that q equals 0 means that you're at qc. Q is the deviation from qc. So these are rolls with the right wave number, the one that the system wants to do. You have to go to higher mu, and that's this picture here. With higher mu, you create rolls with different wave numbers that the system wants to do less. What are these other curves? These other curves correspond to these formulas here. As a function of mu, they correspond to these formulas. And we notice that when the roll is born, when the q equal 1 roll is born, sigma 1 plus is positive. So it's born unstable. Poor thing. Here it is at birth, and it's unstable already. Not very good for it. And that's what you see here at q1. This one here is born, yes, okay, but this curve here, this one that I'm pointing at here, the solid curve, is when that eigenvalue changes from being positive to negative. That eigenvalue is positive all the way from here to here. No worries over here for the Q0 one, because that curve goes dotted below and you're above it. So that eigenvalue, there's no problem for him. He's above all the curves. But he is below this curve, and he doesn't go stable until a higher mu. He's born unstable, and now he stabilizes. So too, he is born unstable, but he has to he stabilizes here and stabilizes again. Let's look at how that works. It's a little complicated.